Assalamu alaikum, everyone. So I'm Dr. Abdullah M, and today I will be presenting on the topic of control engineering of nonlinear systems. Okay, I hope my screen is visible to all. Okay, so let's get into it. So these are the contents of the presentation. We'll start with the introduction of what is this nonlinear control and what is how it is used in the world, and we'll see how different techniques work, and then we'll see how these are being used in some of the systems. We'll look into some of the case studies where these nonlinear control techniques are applied, and we'll see what are the challenges and the future of this nonlinear control. Okay, and then we'll conclude the presentation with the conclusions. Okay, so, well, what is nonlinear control? It is basically a branch of control theory that deals with systems governed by nonlinear equations. Okay, so this is the technical definition. So, if I were to explain it with some better non-technical words, if there is a task that is simpler, you can consider it as a linear system. For example, here's a robotic arm. If the task of this robotic arm is just to grasp an object at a very low speed, you don't care, well, it takes 5 seconds or 10 seconds to grasp an object. You just give the command to the robotic arm and it will just go at a very slow speed, okay, and see, okay, there's the object, and it will use its claws to grasp that object and go to and put it somewhere else or go to something else or do whatever it was supposed to do. So we can consider it as a linear system. Okay. So if the task is very simple and straightforward to do, it could be a linear system. But if you increase the complexity of the task, okay, if you say, for example, you have multiple robotic arms and you say that when I move my fingers, the fingers of this robotic arm should move exactly like my fingers with the exact same speed. There should not be any delay, and it should be able to punch at a high speed. You should do this and that and this and that. If you increase the complexity of the task, if you increase the sophistication of the system, for example, here there's just a claw that can grasp an object, but in the figure below, you have increased the sophistication. You have included fingers; they can do much more precise work. Maybe some of you have seen some robotic arm brain surgery things as well. You have increased the sophistication to a much higher level. So when you increase the complexity and sophistication of a system, you are moving towards a non-linear system. Okay, so in simple words, linear systems behave linearly and you can predict the output. For example, a linear system is an example of a linear system is this, that you're increasing the volume of a speaker using a tunable potentiometer. Okay, so you just rotate that potentiometer and the speaker's volume will increase. You rotate it anti-clockwise, it will decrease. You rotate it clockwise, the volume will increase. So this is an example of a linear system. The task is very simple and you can predict. If I were to say that what will happen if you rotate it clockwise, you would say the volume will increase. You can predict it because it's a linear system. But if I say, uh, if I say a, a high speed plane, a high speed drone or UAV system is passing by a specific tree, what will happen to that tree? Will it be blown away by the air, or will it break down, or it will just shake a little? What will happen? You cannot say anything about it. You will say, well, we have to see for that, because it is now represented using very, very complex mathematical equations. So these are nonlinear equations which you cannot predict. You cannot predict the behavior because it may respond according to your prediction or it may not. It was performing to some extent about in the direction that it was performing previously, and it may change its behavior at any instant of time. For example, humans are nonlinear because if you're talking to someone, he's happy, he seems happy, instantly he may turn into an angry person. Okay, So you cannot predict what will be the output. Okay, so this is the basic idea between linear and nonlinear control, the linear and nonlinear systems. And if you think about it, all all major real life complex systems are nonlinear systems. Okay, very limited and some very simpler systems are linear systems. Okay, so often encountered in real scenarios, these are robotics, power systems, grids, electric vehicles, the UAV systems, even electronic equipment and computers and a lot of things. They all behave in a non-linear system. Okay, so moving on, so why non-linear control matters? Linear control techniques inadequate for many modern systems. Okay, so since modern system here indicates that we are moving towards something that is more and more sophisticated day by day. Okay, so well, if it is more sophisticated, it can do a lot of things. Then yeah, it will have a non-linear nature, and linear techniques will fail there. Okay, so we need something good that can cater for these unpredictable outcomes. We need something that can control these unpredictable outcomes in accordance to our requirement. Okay, so controlling something means that it should do what you want it to do. Okay, if it is unpredictable and it can do anything it wants, you need really, really good controlling strategies to control those things. But if you know, well, this is if I do this system will behave like this. You can just use linear control system techniques because it's simpler to control. Okay. So the non-linear techniques offer precise, optimized control for complex, unstable environment. Okay. So while we have a lot of challenges in this control, nonlinear control domain. We do not know the behavior, how it would behave. The behavior is unpredictable in nonlinear systems. Well, if it's a linear system, you just exactly know, okay, if I do this, that will happen. For example, if you are turning a light of the room on, you just click on the switch and the light will turn on. That is an example of a linear system. You know, if I do this, that will happen. Okay, but a nonlinear system, you cannot predict what will happen in the output. So it is really, really difficult to control that. So we have local and global stability issues in nonlinear control. So this local and global stability indicates that well, the stability here refers to that the system that exists is stable or not. Okay, if I make this robotic arm and this robotic arm explodes after 15 minutes, 20 minutes, well, the system was not stable to begin with. So there's no point in doing any of the work using a system if it's not going to be stable, right? So, well, we have this issue that it is local stable, meaning that it is stable for some of the operations. It is not globally stable. It is not stable for all types of operations. If you are operating the robotic arm at low speed for certain functions, it is good to go. You can do everything, anything you want within that range. But if you want the robotic arm to like maybe work at a faster rate and go to extreme ends to pick up objects and really, really fast, while the robotic arm will fail because it does not have global stability. And we can have multiple equilibrium points. Well, that is a more little technical term. If anyone is interested, what is this equilibrium points and how we have multiple, well, we can go into the detail and see how this multiple equilibrium point creates problem in a nonlinear control system. Okay, so since it is a technical topic, and I will try to make it more generic, and so the different domain audience can understand it a little better. Okay, so now we shall see what some of the control techniques that are involved in controlling these unpredictable systems. Okay, so the knowledge systems is something that we cannot predict what it will do. So we don't just need to predict it, we need it to control it as well. Okay, so here is an example of a linear systems behavior. This blue line indicates that uh, with respect to with respect to time, let's say, it is showing a same type of behavior, that it is constantly increasing with respect to time. Okay, so if the time is increasing on the x-axis, the amplitude of the signal is increasing on the y-axis. Okay, so this red line indicates that the system is nonlinear. If if we have a system that was increasing at some point for some time, then we saw that suddenly it's decreased. Okay, the output decreased for no reason. We just went through time, and it was supposed to increase and keep on increasing, but due to whatsoever the reason, whatsoever the non-linearity in the system, it changes behavior. So once it was decreasing, we predicted, okay, the output is decreasing, it must decrease. Then it became stationary. It did not decrease anymore. Okay, for some time, it was stationary. Then just when we assumed, okay, the output is now stationary, it started to increase again. So nonlinear systems can behave really, really in a way that is unpredictable. Okay, so we just don't need just to consider the output that we may get. We need to control it. So these are some of the, among many, these are three of the nonlinear control techniques that are being used by a lot of researchers in this domain. And first is this Lipnov-based control. Okay, so this Lipnov-based control, what it does is that uh, we can have a stability analysis through energy-like functions that provide the information about the energy of the system. So if you understand how much energy exists in a system, for example, you have a generator and you understand how much watts it can provide, how much equipment or loads it can turn on, you can have a lot of decisions. You can have a lot of better decisions based on this information. So if you understand the energy of a system, you can provide more thorough analysis of different scenarios. So in the nonlinear control domain, what we need is two most important things. The first is the system should be stable. Okay, if the system blows up after a certain time, there is no point in doing any of the work. Okay, second thing is the system should be controllable. It should do what you want it to do. Okay, if there is a system that will not blow up, but it will never obey you, well, humans do not want it. Okay, so we want everything to obey us. Okay, whatever we make, the computers we make, the systems, the hardware, the technology, whatever we make, we want it to obey us. It should follow our commands. Okay, so this Lipnov based control, well, it tries to make it do what you want, but it more focuses on this stability criteria. Okay, so you can give a command that may blow up a system. Okay, so this Lipnov-based control more focuses on how the system should remain stable whenever you are giving it some command. Okay, so this is a very vague and non-technical description of this Lipnov-based control. So then we have this sliding mode control, which is a robust control technique, and it is used in uncertain and disturbed systems. Okay, so for example, if I am balancing a stick on my finger, and I say this is a system, and this should remain balanced, so I can use a sliding mode control instead of and design a robotic hand, and instead of my actual human hand, I can just remove this hand and use a robotic hand and put a finger on it. So this robotic hand will move left and right, forward and backward to balance a stick on top of it. Okay. So if you were to disturb this system, if you were to touch the robotic hand or put a disturbance to this stick, it will make it unbalanced. So here, sliding mode control technique will behave really good. It's a theory that caters for these kinds of disturbances. Okay, so if you disturb a system, of course, the probability of it being unstable or fail or well, not do what you want it to do is really, really high if you provide a disturbance. Okay, in that scenario, sliding mode control is a really good technique. Okay, And there are other systems while they continuously need something to control themselves. Okay, there are systems that you just give a single command. For example, a PC, you can just if you want to turn on your laptop, what you do is click on the power button and it will turn on. Okay, but there are systems that need continuous control. Okay, they need continuous commands. What to do now, what to do now, what to do now, what to do now. So this Lyapunov-based control is a recursive design method, and it keeps on giving commands to the system so it remains stable and do what you want it to do. Okay, so it is effective for multivariable systems. Multivariable systems are the systems in which there are multiple variables involved. For example, in a robotic arm, well, there's the battery that it should use. There is the motors that it should use. There is the material of the robotic arm it should use. So there are multiple variables in the system. Okay. Okay. So if we talk about the Lyapunov function, well, it is a scalar function representing the system's energy. What we do is that we use the Lyapunov theory. The crux of the Lyapunov theory is that if the Lyapunov was a person that stated that using mathematical proofs, he said that if the energy of a system is decreasing, it will ultimately become stable. And we want our systems to be stable. In order to control them, they should be stable in the first place. Okay. So if the energy of a system is decreasing, it should be stable. How do we check that? We represent the system energy using a scalar function, and we perform the Lyapunov stability criteria and see if the energy of the system is decreasing or not. What this information gives us is that it guarantees that the system will remain stable and it can provide information and very accurate information for complex and really, really complex systems. So there are other methods to determine if the system is stable or not in linear systems. Okay. So if we talk about the key features and applications of the sliding mode control techniques, while it is a robust, it is a technique that provides robustness to model uncertainties. Okay. So what we do in the control engineering domain is this, that we design systems, right? We design systems using a model of those systems, and we perform our analysis based on those models. So these models are mathematical equations that represent some real system. So we do not, every time we want to work on something, we do not actually have that physical system right in front of us in the form of a hardware. So we do not have the hardware prototype in front of us, right? And what we have is that those mathematical equations. We say that these mathematical equations represent that system, right? So those mathematical equations might not be 100% accurate, and they might not represent 100% of that system. So what we would say is that, well, there might exist some uncertainties in the model that we are working. Okay, so if I have a robotic car, okay, an electric vehicle, and I use mathematical equations to represent the behavior of the electric vehicle. Well, those mathematical equations may represent 90%, represent the behavior of this electric vehicle up to an accuracy of 90%. There exists an error of 10%. I would say that the model may have some uncertainties and it is not 100% accurate. Well, what's the solution for this? Well, do some more experiments and make it a 100% accurate system, accurate model. Okay, and then work on it. Or use sliding mode control. It is robust to model uncertainties, meaning that if you provide somewhat wrong information about the system and you design it, you use this controller, it will still work. Okay, so it uses a discontinuous control signal based on a switching action. Well, it's again a little more technical to the control engineering domain people. If there is someone in the audience, I would be happy to discuss the detail. Well, I'll just give a big idea. The controllers work by providing some kind of signal to the system. Okay, so the sliding mode control works by providing a highly fluctuating switching signal. It's like the turn off, turn on, turn off, turn on, turn off, off and on, off and on, off and on at a very high frequency. And this Well, if you understand the digital logic, this is how the bits are transferred, and this is how everything works in the digital domain. So controller also gives some PWM signals, and based on this, turn on for those much seconds, turn off for this much seconds, turn on for that much duration, turn off for this much duration. So this decision is everything. Okay, so it this decision, give the energy for this certain amount of time, don't give the energy for this certain amount of time. So this decision is everything. Okay, sliding mode control gives this decision based on its working. Backstepping gives on its own, it gives the decision based on its understanding. Lipolov redesign and other controls, every controller gives this decision uh, about providing the energy for how much duration and taking away the energy for how much duration. Based on this decision, the performance of the system is determined. Okay, so it is used in UAVs, unmanned aerial vehicles, automotive control, renewable energy systems. It is widely used in grids and solar panel control, wind turbine control, fuel cell, hybrid vehicles, and a lot of things. Okay, well, there exists a chattering effect because of this highly switching on and off. Well, what we encounter is this something, a chattering effect that is, well, it is more technical, and if anyone is interested, I would be happy to discuss what is this chattering effect. I'll just give a big idea that this chattering effect may physically damage our equipment because we are giving, we are giving such a high frequency switching signal to the hardware that our capability of those, for example, MOSFETs or some electronic equipment may get burned because of this highly fluctuating decision. So it needs to like well, turn on a system and turn off a system thousands of times in a second. So if it is doing a lot of work, it may damage itself. The electronic equipment, our hardware may damage itself because it does not have the capability to do this much of work that this controller is telling it to do. So that is our chattering effect. Okay, so this is what we wanted was our state to come towards this sliding surface and go to this desired point that we wanted it, but it may encounter chattering over on the way. Okay, so if we talk about the backstepping and the key features that it provides, well, it breaks down the control problem into subsystems. Okay, so we have some electrical or mechanical system, and we get some information from that system, and we give it to the controller, and the controller has some of its own parameters, and this controller based, well, every controller is a mathematical equation. Okay, so that mathematical equation computes a decision based on the information from the system and based on its own theory and design. It gives the signal to the system, and the system in accordance with that works. And we every time we keep on doing this. Okay, this it gives a signal and see what's the output. Okay, that's the output. Now I will give this kind of signal. Okay, that's the output. Now this kind of signal, and the output, it ensures that the output is what you want it to. Okay, whatever you want, the output of the system, it will keep on giving signals again and again and again, so that ensures that you get what you want. Okay, so it breaks down all of those. If there's a highly complex system, for example, if I have grid that has a solar panel, that has a wind turbine installed into it, it has a fuel cell, and it has a, well, that's enough. Okay, so if it has three sources, well, it will break down these three sources and stabilize them individually. Okay, and keep on stabilizing. So it will work on solar panels, and it will work on wind turbines and fuel cell, and combine overall the system would be stable. So, well, the advantage of using this backstepping control is this: it is a highly flexible, suitable for multi-input systems. Okay, so if it's a linear system, it's a very simple system. Well, a single input system, well, you can use other controllers. And not all control techniques have the capability to work with this multiple input system. An example of a multiple input system is that driving an aeroplane while you, or we'll just go to something simpler. Okay, so driving a manual car, well, you do not need you don't have to give a single input. Here you have to give multiple inputs to the system. You have to press the race You have to turn the steerings. You have to put something in gear. Okay, you have to put the gear into first position, second position, or whatsoever. So steering, gear, race, clutch, brakes. So you have to give multiple inputs to the system for it to work. Okay, so not all control techniques have the capability to cater for these multiple inputs, and based on these multiple inputs decide what to do next. Okay, so backstepping control is a really good technique if you have multiple inputs in your system. So it is used in aerospace and robotics because mostly these have multiple inputs, and they have a lot of systems, subsystems in them, and we can use this technique really good. So if we talk about the real world applications of these nonlinear systems and this nonlinear control technique, while nonlinear controls are being used in biomedical engineering. Okay, so nonlinear control is used for chemotherapy, it is used for tumor solutions, it is used for prosthetics, it is used in pacemakers. If we talk about the renewable energy, nonlinear controls you are used for controlling wind turbines, the solar inverters, the fuel cells, the generators, the hybrid energy systems, and so on. It is used in unmanned aerial vehicles for attitude and trajectory control. If you want your flying vehicle to go left, you can use nonlinear control techniques if it's a complex system. And mostly all UAV systems are really, really complex systems. So if you have an electric vehicle, for example, that Tesla is an electric vehicle, while you can, the major part, the heart of this vehicle is this battery management system. So you can use non-linear control techniques for battery management system for torque control, how much torque should be induced in the motors so that it can just take off at a really fast rate. We will talk about power grids. Well, it is used to for stability enhancements in smart grids. While if there is a lightning strike at the system, or if there is some fire in the system that it cannot provide enough energy, uh, too much energy or too much less energy, or any kind of other kind of disturbance in a grid, well, your system, your whole city might be affected due to that. You can use nonlinear control systems to make those complex grids more stable in case of some event. Okay, so these are some of the applications where this nonlinear controls is being used. Well, if we talk about other applications, any real life system that is advanced and it can perform functions that amaze you, while it's a nonlinear system, and nonlinear techniques are used in 99% of those systems. Okay, so this is just to name a few. These are few of the different kinds of domains. So we have a case study here. Okay, so here an article in this journal Expert Systems with Application was published, and it used this condition adaptive barrier function double integral super twisting sliding mode control. Okay, so we had the sliding mode control, and this is a really advanced form of this sliding mode control. It was used for trajectory tracking of a quadcopter. This quadcopter is a UAV system, so for its trajectory tracking, a non-linear control technique was used, and it was published just recently. Okay, so here we see another non-linear control technique, the condition-based robust non-linear control. It was used in an electric vehicle with saturated control actions. Okay, so what this person did was this: there were three sources: the fuel cell, the ultra capacitor, and this yeah. So two sources: fuel cell, battery, and ultra capacitor, and these three were integrated with each other to provide charging for the hybrid electric vehicle. Okay, so you had this electric vehicle, and it works on battery. Of hybrid can work on both. So it needs to recharge itself. Well, to recharge, you need to provide it electricity. So this person designed a system, okay, and it used three sources for the design: the fuel cell, a big battery bank, and ultra capacitor. So well, you can't just directly use a fuel cell and plug it to the electric vehicle. Well, you need to stabilize the voltages and make them come to the level that this electric vehicle wants. Well, for controlling all of this and creating all these complexities and the non-linearities in the system, a nonlinear control technique was used by this author, and this was also published in a Journal of Energy Storage. It's an Elsewhere journal. Okay, so for charging an electric vehicle, here is an example of how a nonlinear control technique was used and published. So if we talk about the biomedical engineering domain, well, there is a lipno-based nonlinear controls for chemotherapy of brain tumor. Okay, so it used Lipnoff redesign technique and sliding mode and terminal sliding mode. It used three control techniques and applied them to the system. And then it compared the performance and showed whether Lipnoff redesign was better or sliding mode was better or terminal sliding mode was better. Okay. So you can, the researchers do this as well. They apply multiple techniques, multiple nonlinear methods, because a question may arise in your mind, which technique is best? Well, there's no technique that is best. One technique might be best for brain tumor chemotherapy, but this same technique might fail in an electric vehicle. And some other technique might be best for electric vehicle and it may fail in a brain tumor chemotherapy. So it depends from system to system which technique is best. Okay. So it used multiple control techniques and provided the comprehensive comparative analysis of those techniques so that the researchers and the world would understand better. Okay, if I want to work on this kind of system, well, here's the person who worked on this domain, and it says that the Planck controller is the best, so I would use that. Okay, so in order to minimize the number of brain tumor cells to maintain a safe amount of LD to keep immune cells above a certain value and ensure the use of suitable amount of drug for therapy. So you're providing chemotherapy. If there's a brain tumor in the system, you're providing the chemotherapy. Well, how much chemotherapy should be applied for how much duration? This decision is not easy to make. Okay. So based on some data from the past, you can guess, but you can use nonlinear control techniques to accurately accurately get the answer. If there exists a decision like this, how much of something should be given, should be applied, should have a value for how much duration? How much for how much duration? These two statements can be answered by control techniques. Okay, any control. The aim of the controllers is to answer these two questions. Okay, so I'm giving a medicine to someone. How much medicine should be given? The quantity of medicine for how much time? For 1 day, 2 days, for 1 hour, 1 second, for a year? What should be the duration? And what should be the magnitude, the dosage, the amount of something? Well, different control techniques will give you different answers, and nonlinear control techniques are always proved that they give more accurate answers, and they give answers based on an output that you want. Okay, you will tell it, I want this person to be healed, I want this brain tumor to be gone. Now tell me, how much chemotherapy should be applied to for how much duration to the patient. Okay, so you give this information and you use maths and mathematical equations to first simulate what will happen if I do this, what will happen if I do this, what will happen. You simulate your results and verify them. Okay, now the patient will be recovered after 45 days if you do this, this, and this. Okay, and then well, here you got the publication, and if well, any lab who is working on this chemotherapy can get information from this nonlinear controller designs. Okay, so here is another example of a biomedical engineering application of this nonlinear control technique. So they used sliding mode based controllers for automation of blood glucose concentration for type 1 diabetes. Okay, so there are multiple types in diabetes. So for type 1, well, how much, based on the concentration of glucose, how much insulin should be injected? Well, how much for how much duration? How much should be, how much insulation, the amount, the concentration, the magnitude of the insulin, and the duration of this insulin should be injected into the patient. Again, we are getting the same question. So they use this sliding mode based controller to answer this question. And Sliding mode is a nonlinear control technique. If you use any kind of nonlinear techniques, you expect the answer to be really good, really accurate, and you cannot just guess it. Okay. So based on some mathematical proofs and mathematical equations, maths never lie. Okay, maths is the absolute true language of the universe. It can never lie. Okay, so based on some really good mathematical proofs, you understand, okay, I have to give this much medicine for that much duration, and the diabetes will decrease, go away, or you will get whatever you want. Okay. So based it keeps on deciding, okay, now give this much amount for this much duration. Next day, give this much amount. It keeps on giving you new information based on the level of glucose in your blood. So it keeps on getting feedback from the system as well, and it keeps on giving you updated decisions based on the behavior of the system. Okay, so if you are eating a chocolate, well, the glucose level in your body, well, you cannot predict it how much it would be. If you eat a biscuit, well, you cannot predict how much exactly the concentration of glucose would be in your body. So if you can't predict the output, we can consider it as a nonlinear system. You don't know what it will behave. So for a nonlinear system, how would you control this glucose concentration? How do you know how much glucose is in your body, and how much insulation should be injected so that this glucose is not too much less, not too much higher than the average value, and you should be exactly on a normal average value? Well, you don't need to worry about any of this. Sliding mode control or this nonlinear control techniques will do this job for you. Okay. So here is another example of this nonlinear control technique in renewable energy. Okay. So they use this optimized nonlinear control technique for fuel cell, supercapacitor, battery, hybrid photoelectrochemical, and photovoltaic cells. So they use multiple energy providing sources, and all the function of all these sources was to provide electricity to you. Okay. Well, there may exist some transients in the system, and you may get irregular voltage levels or other disturbances in the system that may burn your equipment. Well, you need to cater any kind of disturbance and provide a stable output. Well, here they use nonlinear control technique to stabilize the system and give you best energy possible in the output. Okay, so this was also published in journal. It was just recently, 2020, last year it was published. So as we're moving forward with respect to time in the new era of technology, day by day, more and more advanced and more sophisticated systems are being developed. Hence, this nonlinear control and this engineering domain is become one of the most important topics for anyone to study, because if you want to design something in hardware, well, you cannot get it done without these methods. Here's another example of this magnetic levitation system. So some of you might have heard about bullet train, where it is used in Japan and a lot of other countries. So this bullet train is also works on this magnetic levitation system. So they use this integral backstepping and synergetic control. Two control techniques were used for magnetic levitation system, and they stabilized the levitating object using intelligent decisions. Okay, so this is another example. So here we have another example of how these nonlinear control techniques are used in AC/DC microgrids. Okay, so a lot of you might have an idea what microgrids are or grids are. Well, the grid is something that has a lot of multiple types of energy sources, and it can provide you electricity. Okay, so they used integral terminal sliding mode control technique. And there are a lot of techniques that are used for a lot of systems. These researchers use this integral terminal sliding mode, that is an advanced form of the sliding mode control. Okay, so they use this to stabilize this hybrid AC/DC microgrid. So the purpose of this case studies was to give you an idea how this nonlinear control techniques are working in various different kinds of domains. Okay, So if we talk about the challenges in this nonlinear control, if it is so much important, then why do linear control exist, and why not completely shift towards this nonlinear control? Well, it requires a lot of computational power, and it has complex requirements for computing, and a lot of cost is involved. Well, you do not want to overkill something, right? So if the purpose was to kill a bee, you do not need to develop a cannon for that. Okay. So nonlinear control technique is the example of a cannon, and the purpose of the aim of this development, if it's to kill a bee, well, what's the point? It's an overkill, right? So uh, the extra cost involved and the computation and the more complexity and the effort that you would put in developing this cannon is kind of like a waste. All right. So whenever you have to design a simpler task, we go ahead and do use this linear system. Well, when you increase the sophistication, when you increase the system specs, then go for it. Go use nonlinear controls. But if you increase the sophistication, of course, the cost was increased because these these complex mathematical equations require higher computational power. Okay, so they are more complex than linear systems. The controller is not easy to design. Okay, so these are non-linear mathematical equations that require a lot of different kinds of complex methods to solve them. So we have model accuracy problems. Nonlinear models are harder to develop and validate. Like I gave you an example. If there is an electric vehicle and you have mathematical equations representing that electric vehicle, well, they might represent the behavior up to an accuracy of 90%. While there's still mathematical equations cannot just give 100% information about the system. Okay, whatever they give the information, that is 100% accurate, but it might not give you all information about the system. Okay, so if you're not taking everything, all information about the system, the decision might not be very good by a controller. Okay, so in the first place, those mathematical equations are not easy at all. There are a lot of certain methods, and those are complex methods to convert a hardware system to mathematical equations. So these equations are exactly representing the behavior of that hardware system. So it is really difficult to do that as well. Okay, and then we see that there was an effect of chattering effect in sliding mode control, and there are other effects and other problems as well when you use nonlinear control techniques. Well, the chattering effect is mitigated by using some advanced variants, as you saw in some of the publications that I just showed you, that they used advanced variants of sliding mode control to cater for the problems that come with this one of the techniques, the sliding mode control. So if we talk about the future of nonlinear control, well, it's not just we are using nonlinear control with AI and machine learning for much better control, for adaptive control that can change its decision in a much more better way in accordance with the disturbances or whatever the environment is. Okay, we can use multiple controllers, combination of linear and nonlinear controllers for more efficient control. If the task is simpler, go use the linear controller. But if for the same system, now the task is something complex, well, we'll just shift to nonlinear control. So the system is more stable. It performs better because better decisions are being given to this same system. Okay. So by combining linear and nonlinear techniques, what we are doing is we are not overkilling something, right? But if required, we have the capability to kill a bigger bee, right? So we can use this quantum computing. It has the potential to solve nonlinear control problems faster, right? So quantum computing is one of the most promising domains for the nonlinear control designs, because complex higher order mathematical equations are not easy to compute, and they may take a lot of time to design. So we go for approximations which are not very accurate in certain scenarios. So if we have these quantum computers, they can be used really good. Autonomous systems, nonlinear control as the backbone of fully autonomous vehicles, drones, robots. So systems that can make decisions on their own. If we're talking about decisions, nonlinear control techniques will give you the best decisions. So to conclude the presentation, while nonlinear control is essential for modern engineering challenges, okay? So it is not just something, yeah, you can use it. It is an essential part. If you want your system to be good, really good, You need nonlinear control. Well, it is used in a lot of different kinds of industries. While future innovation will further enhance the capabilities, okay, of this nonlinear control domain. So to sum up, the final stance would be the nonlinear control is not just about managing complexity. It's about unlocking the full potential of today's advanced systems. Okay, if you limitize some system, well, a linear technique may work. If you are utilizing the full potential of a system, well, if you're utilizing it, every feature of that system, well, non-linear control, you need it. Okay. So that's pretty much it. And